Hello, Algebra 2 Honor students. This is going to be Unit 8, Day 2. Some more synthetic division coming your way today, which is good. I think we need a little bit more practice until we kind of get a sense as to what that whole process is all about. So given f of x equals x cubed minus x squared minus 4x plus 4, I want you to answer a few questions for me based on what we've done with synthetic division so far. Question 1 is x equals -3 a root. So think about how you're going to use synthetic division to test whether or not x equals -3 is a root. Now, part B is a slightly different way of asking a similar question. Is x plus 1 a factor? Think about what you're going to do in synthetic division to determine if x plus 1 is a factor. Part C, compute f of -3 and f of -1. So that's something we could have done way back in the beginning of the year. F of -3 is just plugging in -3 for the x's, right? F of -1, same thing. Plug in -1 for x, see what the output is. And then what conclusions do you think we're going to make about that? I would highly recommend trying this on your own because I'm about to show you those answers. So I would hit pause in the video, go and try to answer those first 3 parts. And if you do them correctly, I think you'll be able to make some good solid conclusions. If you're unsure, well, you'll just hit pause. And when you hit play again, you'll wait for me to go over the appropriate conclusions here. What have we got? Ready? X equals -3. Is it a root? The answer is no, it is not. So when I do the synthetic division, right, bring down the first number, multiply by the root, add it to the number above, we got a remainder in the end of -20. Okay. And even though the remainder is not 0, today is all about figuring out if the remainder is non-zero, is there other information that we'll know about the graph of f of x? All right, part B, is x plus 1 a factor? I hope that you tested -1 as a root based on what we talked about yesterday. If x plus 1 is a factor, that would be testing -1 as a root. The answer is no again. The remainder should be 6 when you use synthetic division to test -1. Part C was to compute f of -3 and f of -1, and if you plug those in, you get -20 and 6. Those numbers sound really familiar to me. -20 and 6. Whoa, those are the remainders from synthetic division. So what we just determined here, and I hope you'll trust that it will hold true for every example, is that the remainder from synthetic division is the same as the function value at those x values. So what we're determining here is that when you plug in a number for x, what does this number represent? It's the y value on the function. Even though I didn't get 0 as a remainder, the point -3, -20 is on the graph of this function. The point -1,6 is on the graph of this function. So that brings us to something called the remainder theorem. And what the remainder theorem formally states is the following. If f of x is divided by a factor x minus capital R, then the remainder is f of capital R. So when I do that synthetic division, whatever that capital R is, the root that I'm kind of testing, the remainder will always match the function value at capital R. And that's what we saw in the examples right up here above. So that's pretty critical to us. And it doesn't seem like that exciting of an idea, especially when I don't get 0 as a result, because we like finding roots in this unit. But it's going to be very helpful for what we now conclude in an additional theorem. Okay. So one other quick note about that is that the point R comma f of R is on the graph. So I've already mentioned that. So what we're getting into is if I were to plot those 2 points, if I were to plot -3, -20, and -1,6. What do I know about plotting those 2 points on this graph? Well, to get from -3, -20 to the point -1,6, we know that we're going to have to cross the x-axis somewhere in between that connection. So a good conclusion to make is based on where those coordinate points are located, there must be a root between x equals -3 and x equals -1. So not only is this remainder theorem kind of nice in terms of knowing that there are y values on the function, But the other major conclusion out of today is that when you see the y value go from a negative to a positive, or vice versa, if it went from positive to negative, I know that there has to be a root somewhere in between x equals -3 and x equals -1. We have to cross the x-axis. So when we're doing synthetic division, if I see a sign change like that, if I see a sign go from a negative remainder to a positive remainder, the implication is we're going from a negative y value to a positive y value, which means that there's a root in between. And that is known as the root location theorem. So here's what the root location theorem states. Okay, pretty formal definition here, but it says if A and B are non-roots, okay, so capital A and capital B are not roots of f of x, such that f of A and f of B differ in sign, right? F of A was -20, f of B was +6. Then there exists at least one real root between A and B. Have to cross the x-axis to go from a negative to a positive y value. So when we eventually get to a point where we're starting to test different roots and we're saying, what would make sense to test next? Maybe it's -2. Well, I mean, based on my graph, it doesn't look like it crossed there. It doesn't have to be midway in between. Maybe it's -1.5. Maybe it's -1 3/4, something like that. But I know that there has to be a crossing somewhere in between those two roots. Okay. These will be pretty important theorems to us as we go forward, and I start giving you less and less information about these polynomials. Okay. So let's go ahead and do some more synthetic division practice, but I'm going to up our game a little bit. And by upper gain, I mean I'm going to give you a 4th degree polynomial. So for our first example today, I'm going to find all the roots. Oops, not roofs. How about roots of 6x to the 4th minus 19x cubed minus 25x squared plus 18x plus 8 equals 0. Oh my goodness. Okay, we got a 4th degree polynomial here. I'm going to give you 2 of the roots though, given 4 and -1/3 are roots. Now in the future, I may not always give you 2 roots, but in this case, I'm going to give you 2 of the roots. One thing we should probably discuss that maybe we haven't up until this point is that a 4th degree polynomial will always have 4 roots. So the degree of the polynomial is equal to the number of roots that the polynomial has, which I think should make sense, right? When you solve a quadratic, you always get 2 solutions. Solving a cubic, you'll get 3. 4th degrees, you'll get 4. All right, so how am I going to find all 4 roots? Let me get started by showing you that if I test 4 in synthetic division, it should be a root. And synthetic division works the same way, whether it's a 4th degree or any degree polynomial. So we get 6, -19, -25, 18, and 8 are the coefficients. We're going to bring down the 6, multiply by the root, so that's 24, right? 6 times 4. Add it to the -19 above to get 5. 5 times 4 is 20, plus -25 is -5. -5 times 4 is -20, plus the 18 above it is -2. -2 times 4 at the end is -8, plus 8 is 0. Here's the deal. If you don't get 0, you did something wrong, because I'm telling you 4 is a root. So 4 is a root, definitely got to get 0 in the end. Now, if you compare this to what we've done earlier in the unit, when you divide something into a cubic, these coefficients used to be a quadratic that you were left with, something with x squared. But you're now dividing a linear factor into a 4th degree polynomial. So what are we left with right here? This is not the coefficient of x squared, it's the coefficient of x cubed. This is the coefficient of x squared. This is the coefficient of x, and that's the constant that would be at the end. So we're not quite down to a quadratic yet. Quadratics are nice because we know how to solve them. We can factor them. If it's not factorable, we got quadratic formula on our side. You need to do a step that sounds sad, but it's really not. It's actually a happy step. It's called depressing the equation. And like I said, depressing sounds like it's sad, but depress in this instance just means we're going to take the equation from a fourth degree, shrink it down to this cubic that we have left, and test negative 1/3 as the next root. So that's why I had to tell you two roots, because when I test negative 1/3 as a root with these coefficients, okay, you don't need the 0 from the remainder, just these 4. When I test that second root in a cubic, then we'll shrink it down to a quadratic. So we're going from a fourth degree to a third degree. From a third degree, one more root test will get you to a quadratic. We maybe haven't tested fractions yet, but it won't be too scary. 6 times negative 1/3 is -2. Think of just dividing by -3, right? Add it to 5, that's going to be 3. 3 times negative 1/3 is -1, plus -5 is -6. -6 times -1/3 is +2, plus the -2 is 0. If you didn't get 0 there, you're also in trouble. -1/3 is a root. So we got to find that that's a root. Okay, now we're pretty happy because in the end, I do have a quadratic. This is now 6x squared plus 3x minus 6. And it did say to find all of the, not roofs, but roots up there. So to find all of them, I need all 4. Well, I know 4, I know -1/3. Take that quadratic and solve it. If I'm solving the quadratic, you are allowed to divide this GCF of 3 out if you'd like. So if I divide both sides by 3, I get 2x squared plus x minus 2 equals 0. And just to save us some time and some heartache, I'll tell you this is not factorable. So you can try and factor it. You can do any of the techniques that you know how to factor with the lead coefficient, but none of them will work. So in the end, quadratic formula will be the default to get the other two solutions. So we do x equals -b, which is -1, plus or minus the square root of b squared, minus 4ac, all over 2a, and a is 2. So let's see what we're going to wind up getting here. This is going to be x equals -1 plus or minus the square root of 1, and then this is going to become plus 4 times 2 times 2 plus 16, and 1 plus 16 is 17, all over 4. So altogether, the roots in the end, if I were to make a list, would be 4, -1/3. And then if you want to leave those together, you can, but those are two distinct roots, aren't they? -1 plus radical 17 over 4, -1 minus radical 17 over 4. Those are the other two solutions. If I were to have us make a graph of this, knowing the decimal approximations might be nice here, so that this root at -1 plus radical 17 over 4 is about 0.78. And then -1 minus the radical 17 over 4 is -1.28. So if I were to make a sketch of this graph, we have x-intercepts at -1.28. So that's like right over here. We have an x-intercept at -1/3. That was one of the roots I tested, right? We have a root at 0.78. And then we have a root at 4, 2, 3, 4. So we're going to cross the x-axis once, twice, 3, 4 times we're going to cross. And last thing I want you to think about is because we know the end behavior of the graph, because this number is positive, I know that both ends of the graph will head up. So what's going to happen is you're going to come down through the first root here, go back up through the second root, down through the third, and up through the fourth at the end. And here's, even though it's a rough sketch, that's a relatively complete graph of what we started with just by finding those 4 roots. Okay. For now, I have to tell you some of the roots to get started, but let's try one more like this. And if you'd like to give it a shot on your own, I'd encourage you to do so. But I'm going to go through the solution as I write it down. Okay, our last example is to find all roots of f of x given 4 is a double root. So the polynomial f of x is going to be defined as x to the 4th minus 8x cubed plus 20x squared minus 32x plus 64. Okay, so I'm going to tell you that 4 is a double root. So it occurs twice in our list of roots technically. So when I go to do synthetic division, I'm going to start by testing 4, of course, with these coefficients, 1, -8, 20, -32, and 64. Okay, bring down the 1. All right, let's do the synthetic division kind of quickly here. 1 times 4 is 4, plus -8 is -4, times 4 is -16, plus 20 is 4. This is going to be 16 here, plus -32 is -16, times 4 is -64, plus 64 is 0. Okay, got to get 0. I'm telling you 4 is a root. And not only is it a root, it's a double root. So now make sure you depress the equation, because this is the coefficients of a cubic polynomial. So you're going to test 4 again, since it's a double, but now in the coefficients 1, -4, 4, and -16. So we get, bring down the 1, 1 times 4 is 4, plus -4 is 0. Okay, that's weird. 0 times 4 is 0, plus 4 is 4. 4 times 4 is 16, plus -16 is 0. And had to find it was a root a second time because of the nature of a double root. So what do we have in the end? I mean, this looks a little bit different, but we have x squared, the coefficient is 1. When the coefficient of x is 0, there's no x term in your equation. This is the constant at the end. So when I write the equation, it's going to be x squared plus 4 equals 0. That's the quadratic we would solve to find the other two solutions. So when I go to solve this, you do not need quadratic formula, do you? You could subtract 4 to the other side and then square root, square root. But what is the square root of -4? The square root of -4 is plus or minus, first of all, 2i. So this is a 4th degree polynomial that does not have 4 real roots. It has 2 roots that are real and 2 roots that are complex or imaginary. So the roots you can list as 4, 4, -2i, and +2i, something like that. Or if you wanted to say, and get fancy, to say that 4 is a double root, sometimes you'll see it written as 4 multiplicity 2. Okay, so the term multiplicity just implies whatever the multiplicity is, that's a double root, or there's even something called a triple root. And if you wanted to combine the plus or minus 2i and write those together, you could do that too, however you like. But in the end, we should be able to give in 2 roots for our 4th degree, test 1, get a cubic, test another, get a quadratic, solve the quadratic. We have all of those skills, which is pretty fantastic. All right, that's it for a little bit more synthetic division practice. Much more to come with synthetic division in this unit, but have a great